Now let's try to understand the phase difference in the synchronization of clocks as seen by a moving observer. Okay, and we'll try to again understand this intuitively from the postulates of special relativity and what we've already seen about length contraction and time dilation. So suppose that you have, again, a moving train, okay, and suppose that there are two different synchronized clocks on this train. So according to the train observers, these clocks are perfectly in sync with each other. However, we have seen that according to a ground observer, an observer on the platform, these two clocks will appear to be out of phase with each other. They will both tick at the same rate, that is, time intervals on the train will be the same on both clocks, and they will be related to time intervals on the ground as delta t over gamma. But in addition to this, they will appear to be out of phase with each other. That is, the clocks which are along the direction of motion appear to be further and further behind, and the clocks that are further opposite the direction of motion, that is to the left, those clocks would appear to be further and further ahead. Mathematically, the statement that we have is related to the inverse transformation, inverse Lorentz transformation between S prime and S. You can show by inverting the Lorentz transformation that T would be, as measured by the ground observer, would be T prime plus Vx Vx prime over C square times gamma. Okay, so this gamma factor only tells you about the relative time intervals of a particular moving clock at a fixed location x prime. Okay, so that is, if I take a moving clock at a fixed x prime, that's a particular moving clock on the train, moving with a particular train observer, and therefore the time intervals delta t would be gamma delta t prime for this particular clock. But now what we're interested is in asking if we have two different clocks on the train that are separated by a length L prime, so one clock over here, one clock over here. We want to know what is the phase offset of these two clocks. So the phase offset of these two clocks separated by a length L prime on the, as measured on the train, that phase offset would be a time difference delta t prime offset, which would be V times L prime over C square. Okay, so this would be the apparent offset in the time on these clocks as measured by an observer on the ground. So this is the apparent phase difference as measured by an observer on the ground. And this observer on the ground would see that the clock over here and the clock over here, as measured at the same instant of time according to ground observer's clock. So if the ground observer has a clock here which shows a time t and another clock here which shows a time t, and they peek inside the train to look at the readings on the clocks, they would see a phase offset where if the train is moving to the right, the clock over here is ahead and the clock over here is behind, and the time difference between those two clocks would show VL prime over C square. Now let's try to understand intuitively from what we've learned about time dilation and length contraction, why it is that there should be such an offset. So let's imagine that we are now trying to synchronize clocks on the train. So on the train, or in frame S prime, we have two clocks, two detectors, which are going to register light clicks. And we have a source which will send out light signals to them simultaneously. And this source is sitting at the midpoint between these two detectors, which are at a distance L prime apart from each other. And once these signals reach these detectors, we set both clocks to t prime is equal to 0. So that is, these clocks become synchronized with each other. Now let's give these detectors names. Let's call this detector A and detector B. And let's see what the synchronization procedure would look like to the observers on the ground. Now, from the perspective of an observer on the ground, so that is on the ground in frame S, the detectors A and B are moving to the right with some velocity v, let's say. So A is moving to the right with a speed v, B is moving to the right with a speed v. And let's suppose that we take the instant at which the source emits these light beams, and let's assume without loss of generality, okay, that this defines a t is equal to 0 and x is equal to 0 for the ground observers. And now we know that detector A will move forward and the light beam from the source will move backwards as seen by the ground observer, and at some point detector A will encounter that light beam. And similarly, detector B would have moved ahead. So let me draw this as actually a separate instant of time. So at some instant of time, A receives the light signal. And at a later instant of time, at this same instant of time, A has moved a distance V times delta T1, where this is at a time T is equal to delta T1. And the detector B has also moved ahead by an amount V delta T1. And since the light signals are traveling at the speed of light, as seen both by the observers on the train as well as by the observers on the ground, the light beam would still not have caught up with B. Okay, so the light beam is still not caught up with B. And it would only be later that the light signal will actually catch up with the clock at B. So let's suppose this happens after time delta T2, where A has moved ahead. The light signal has already been absorbed by A or crossed A, and this light signal, which was sent towards B, has just reached B at this point. Remember that the signal was sent from the location x is equal to 0. Okay. And the distance moved by B is V delta 2. So what we would conclude is that the observers on the train would set their clocks to be the same. That is, we see that the observer at location A on the train would, let's say, set their clock to some instant of time. Let's say t prime is t naught here. But it would only be at a later instant of time, as measured by the ground observers' clocks, that B would set their time to t prime is equal to t naught. So the observer on the train is concluding that these events A and B are simultaneous, whereas to the ground observer, they do not appear to be simultaneous. And therefore, it looks like the clocks at A and B have an offset with each other. And the amount of offset is the thing that we really want to determine. So let's clearly label our pictures. So this is at instant t is equal to 0 as measured by the synchronized ground observers clocks. This is at instant t is equal to delta t1 as measured again by the synchronized ground observers clocks. And this is at an instant t is equal to delta t2, again as measured by the synchronized ground observers clocks. Now, the first thing is that we know that the ground observers will see the length of the train, or the distance between observers A and B, to be length contracted. So if this length is L as measured by the ground observers, we know that the length L will be related to the length measured on the train divided by gamma. Or in other words, it would be the length measured on the train times the square root of 1 minus v square over c square, where v is the speed of the train relative to the ground observers. Now, let's look at the instant t is equal to delta t1 and ask what is the distance that the light beam had to travel to get to A. So in order to get to A, this distance is L by 2. So the light beam had to travel, let's write this down, light beam had to travel a distance of L by 2 minus V delta T1 to reach observer A, or detector A. And it travels this distance in a time delta T. And it took delta T1, and it took a time delta T1 to reach A. And since light travels at the speed of light as seen by the observer on the ground will conclude that L by 2, the distance it traveled, L by 2 minus V delta T1, divided by delta T1, the distance it traveled divided by the time it took should just be the speed of light, okay? And we can do a similar analysis for the detector B. In this case, the light beam has to travel a greater distance than L by 2 because detector B has moved further ahead. So it travels a distance of L by 2 plus V delta T2. So the light beam has to travel a distance of L by 2 plus V delta T2 to reach observer B. And it takes a time delta T2 to reach B. So again, since light travels at the speed of light as seen by the ground observers, this distance traveled by the light beam divided by the time it took must just be equal to the speed of light. And now, finally, if we want to know what the phase offset will be between these two clocks, the way to think about this is as follows. So at t is equal to delta t1, when A receives the light signal, they set their clock to t prime is t naught. Now, in a time between delta t1 and delta t2, the clock moves ahead, okay, and some amount of time would have ticked on A's clock. So let's call that time that is ticked on A's clock delta t prime, and that's the time that is ticked on A's clock between the time intervals delta t1 and delta t2. Now, we know that moving clocks tick slower than clocks on the ground. So this time interval delta t prime will not be equal to delta t2 minus delta t1, but rather it would be smaller by an amount gamma. Okay, so the time that would show on A's clock as measured by the ground observer at the location of A would be T prime is T naught plus this delta T prime. Okay, and at this instant B sets their clock because B just receives the light signal from the source. So B sets their signal, their time to T prime is T naught. So A and B, if the ground observers who are at their locations look in right now at their clocks, they will see a phase offset, and that phase offset is by an amount delta T prime. So let's work out what that phase offset delta T prime is. So delta T prime is the phase offset of the train clocks as measured by the ground observers. And this phase offset would just be equal to delta T2 minus delta T1 divided by gamma. So now we can use our equations, the earlier equations that we had used to calculate the light travel time from the source to A and B. So we can use this equation to solve for delta T1, and you can see that this is very simple. What we would get would be delta T1 is equal to L over 2 divided by C plus V. And over here we would get delta T2 is equal to L over 2 over C minus V. Okay, so we can plug in A or small a, equation small a and small b. So plug in expressions for delta T2 and delta T1. And what we would get is that the phase offset between the clocks on the train, as seen by observers on the ground, would be equal to L over 2 divided by C minus V minus L over 2 divided by C plus V, and the whole thing divided by gamma, which is 1 over the square root of 1 minus V square by C square. And so we can write this as now L over 2 C plus V minus C minus V over C square minus V square. And since this is divided by a fraction, we can write this as 1 minus V square over C square. So that gives us L over 2 into 2V over, let me pull this out as C square, 1 minus V square by C square into the square root of 1 minus V square by C square. So writing that more simply, this is L over 2C, sorry, let the factors of 2 cancel out. L over C square. Let's rewrite this like this. So let's write V over C square times L over the square root of 1 minus V square by C square. But now, the length L, as we had discussed earlier, is the distance between A and B, and this distance is as measured by the ground observers. And this distance is length contracted compared to the actual length between A and B on the train, or the proper length between A and B. So the length L is related to the length L prime, but it's smaller by a factor of square root of 1 minus v square over c square. That is, its length contracted relative to L prime. So if we plug this in over here, we have L is L prime into the square root of 1 minus v square by c square. And therefore, the parent phase delay between the clocks A and B would just be v over c square times L prime. And this expression is in exact agreement with what we expected from the Lorentz transformation of the offset between the clocks, or the phase delay, being v times L prime over c square. All right, so now we have an intuitive perspective of, given the constancy of the speed of light to all observers, we now understand why the clocks in the train would not appear to be synchronous and in fact would just have a phase delay.